Hey, Honors Pre-Calc. Today we're going to start lesson 7.4 on the binomial theorem. So we're going to be switching gears a little bit today. We've been talking a lot about sequences and series, so pattern among numbers, and then summing those terms, right? But today we're going to be looking at something called the binomial theorem. The essential question is, how do you use the binomial theorem to determine the coefficients of binomial expansions? We're going to use something called Pascal's triangle to determine the coefficients of binomial expansions. And by the end of this lesson, you're going to be able to look at something like 3a minus 2b to the 11th power and find a specific term of the final answer, multiplying all that out without actually doing all of the work. So for example, we'll be able to find the coefficient of the term that has a to the 6th, b to the 5th. So in other words, what number comes in front of a to the 6th, b to the 5th. In this expansion, we can figure that out using some tips and tricks without actually doing all of the multiplication, because we realized we'd have to FOIL and then distribute like 11 times in order to actually solve this normally. So we're going to learn some tricks today. And so let's head over to the notes. All right, so here we go, lesson 7.4, the binomial theorem. First off, we need to know that a binomial is a polynomial that has two terms, such as x plus y, right? Bi is a prefix meaning two, so it makes sense that it would be two terms. This is the first, I guess, 6 binomial expansions, starting with an exponent of 0. And so when we say binomial expansion, what we mean is that we have a binomial, it's raised to a power, and then we actually expand it by multiplying. So we're going to be looking for patterns in these expansions. And just to prove, that the first couple are true, I wanted to write this out. So if you could write this on your notes as well, that would be great. So let's just say we were looking at, the first one just makes sense. If you raise anything to the 0 power, you get 1. So you're just going to get 1 there. For the first power, nothing changes. For the second power, that's the first time where it's like not completely obvious this is the answer until you FOIL. So if we did that by hand, we would have x plus y times x plus y. And we'd have to FOIL, right? First, outer, inner, last. So we'd get x squared. The outer would be x times y. The inner would be x times y. And the last would be y squared. And we have two different xy terms. So we can combine those for an official final answer of x squared plus 2xy plus y squared. And typically when we write out a polynomial, if we want it to be in standard form, we pick one of the variables and write the terms so that the exponents are in descending order from largest to smallest. So in this case, we picked the x, started with an exponent of 2, then an exponent of 1, and then it's gone. All right, so that is the standard form, and that's the answer that's written down here as well. So let's say we wanted to look at the next line, so x plus y cubed. We could start with x plus y times x plus y, and then multiply the x plus y again, right? So let's just say we're starting with what we already got, x squared plus 2xy plus y squared, and multiplying by x plus y again so that it becomes x plus y cubed. We should end up with this. So let's see if we do. I'm going to have to, instead of FOILing this time, I'm going to have to distribute the x squared to the x and the y, the 2xy to the x and the y, and then the y squared to the x and the y. So let's do that. So we have x cubed, the x squared to the y, it's going to be x squared y. We have 2xy times x, so it's going to be 2x squared y, and then we have 2xy times y, so 2xy squared. Y squared times x is xy squared, and y squared times y is y cubed. If we combine like terms and put that into standard form, we're going to end up with x cubed. We have x squared y plus 2x squared y, so it's going to be plus 3x squared y. We have 2xy squared plus xy squared, so it's going to be plus 3xy squared, and then plus y cubed. And you should be able to see that that matches exactly what's written down here. So I'm just going to ask you to trust that then if we multiply it by x plus y again, and then again, we'd get these next two lines, right? So the whole point of this lesson is to say, doesn't matter what this exponent is, we can find these answers a lot quicker than multiplying by x plus y 1,000 times. So let's first just look for some general observations about binomial expansion. If we look at all 6 of these examples, what is true about all of them? And if we were in person doing this together, I might ask you to look with a partner and find these, but I'm just gonna kind of go over these observations with you. So first of all, we have, if n is the given power, so if we think of this exponent as being the n, there are always n plus 1 terms in the final answer, right? So if the n was 2, we have 1, 2, 3 terms. If the n was 4, we have 1, 2, 3, 4, 5 terms. Makes sense. There's always one extra term each time. In successive terms within one expansion, powers of x decrease by 1 and powers of y increase by 1. Take a look at x plus y to the 5th. The x term always goes down 1 exponent each term. So 5, 4, 3, 2, 1, 0. And the y goes up 0, 1, 2, 3, 4, 5. The sum of the powers in each terms is n. In each term is n. So back in the x plus y to the 5th, in this term right here, we have a power of 4 and a power of 1. That adds to 5. Power of 3, power of 2 adds to 5, etc. That's always going to be the case. And another observation, the coefficients increase and then decrease in a symmetric pattern. So in this x plus y to the 5th, we have a coefficients of 1, 5, 10, 10, 5, 1. They increase and then decrease in a pattern. Same thing happens in x plus y to the 4th. We have 1, 4, 6, 4, 1. Okay, so given that information, this theorem was constructed that is always going to help us to be able to expand binomials. So that's what's going on down here at the bottom of the page. In the expansion of x plus y to the n equals x to the n plus n times x to the n minus 1 times y. It looks a little bit more complicated than it did at the top of the page, but there's this pattern going on. And all that I want you to notice for now, ignore the coefficients going on here. Let's just look at the exponents, right? If the exponent of the expansion is n, the x starts with the exponent n, and then it goes down 1 every time until it's gone. The y starts gone, and then it adds 1 every time. So it starts with a 0, and then 1, and then by the end, there's n y's. So the y is going up, the x is going down. Just like at the top of the page, it's just written out, cryptically, right? In variable form down here at the bottom. And then we have this thing to help us find the coefficient of any term. Coefficient can be represented with NCR, which is known as a combination. We're going to talk about combinations and permutations in a future lesson. Maybe you have studied that before. Those words might sound familiar, but if you haven't, the C stands for combination here. The C is never something that gets replaced. The N and the R get replaced. If you look down at example 1, you'll see we have like 8C2 or 7C0. We refer to this as like 8 choose 2 or 7 choose 0. We'll talk more about why that is in a future lesson. But in any given term, the combination, so the coefficient can be found using n factorial over n minus r factorial times r factorial. R is always the value that is the exponent of the y term. And in general, it's kind of like the term that you're on almost, but we'll get to that. We're also going to be using something called Pascal's triangle to help us remember the pattern. We'll get to that. I've kind of gone over a lot already, so let's just try example 1 first. Find each binomial coefficient. So all we're going to do right now, before we get into some of the crazy stuff, figuring out, hold on, I'm going to pause. Everyone. Just wanted to... All right, so let's try letter A, 8 choose 2 down here, finding the binomial coefficient. Let's just think about the formula for now. So we have n factorial over n minus r factorial times r factorial. So in this question, we're going to have 8 factorial over 8 minus 2 factorial times 2 factorial. And in case you're not super familiar with factorials, 8 factorial means 8 times 7 times 6 times 5 all the way down to 1. So this 8 minus 2, though, becomes a 6. So we have 8 factorial over 6 factorial times 2 factorial. And so I'm going to break down the numerator. So it becomes 8 times 7 times 6 factorial over 6 factorial times 2 factorial. So the reason I did that, right, 8 factorial is the numbers 8 all the way down to 1 multiplied together. 8 times 7 times 6 factorial is going to be the same thing. So the reason I wanted to write it that way is so that now the 6 factorials cancel and leave us with just 8 times 7 over 2 times 1. And if we multiply that out, we're going to get 28. This is just another way of writing 10 choose 3. You can see we have that up here. Parentheses with the number on top and number on the bottom is often used in place of using the letter C. So it's the same thing, but it's going to be 10 factorial over 7 factorial times 3 factorial. I did the 10 minus 3 already this time. So you can see it looks like that. So let's try the same strategy. I'm going to do 10 times 9 times 8 times 7 factorial over 7 factorial times 3 factorial. That way the 7 factorials cancel. And so we're going to end up with 10 times 9 times 8 over 3 times 2 times 1, which is going to equal 120 once we multiply it out. All right, let's look at letter C. In letter C, we have 7 choose 0. So it's going to be 7 factorial over 7 minus 0, which is 7 factorial times 0 factorial. This time, it's pretty easy to see the 7 factorials cancel out. 0 factorial is defined as 1. So we really get 1 over 1 or just 1. And 8 choose 8 is going to be 8 factorial over 8 minus 8, which is 0 factorial times 8 factorial. 8 factorials cancel again. 0 factorial is 1. So once again, this equals 1. Okay, so that's how we do that. I want to look at some patterns here before we get into the next page. So let's take a look at letter A. Since we were choosing 2, since 2 was our R in this first question, the rule is that on top, we do the first 2 numbers starting at 8. And on the bottom, we do the smaller number factorial. So it's always going to be the same number of numbers on the top and on the bottom. We do 8 times 7 on top, 2 times 1 on the bottom. Hopefully you can tell what I'm talking about. In letter B, since we were choosing 3, or 3 was a smaller number, we do 10 times 9 times 8. So 3 numbers on top and 3 numbers on the bottom. The last 3 times 2 times 1. That pattern continues. So let's use that strategy to solve E and F here. In letter E, 7 choose 3 is just going to be 7 times 6 times 5 over 3 times 2 times 1. And that equals 35. So if we do 7 choose 4, it's going to be 7 times 6 times 5 times 4 over 4 times 3 times 2 times 1. So the first 4 numbers and the last 4 numbers, there's a little bit of overlap this time. So the 4s cancel. We get the same exact fraction that we did over in letter E. We're going to get 35 again. In letter G, we have 12 choose 1. So we just have 1 number on top and 1 number on the bottom. We just get 12. And for 12 choose 11, this is going to be a little trickier. We're going to have to do the first 11 numbers on top. So it's going to be 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. And on the bottom, we have the last 11 numbers. So 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And what happens is 11 through 2 all cancel out and we are left with 12 over 1 again. All right, so I want you to notice another pattern this time, and that is if the first number, the n, is the same, then there's kind of like a repeat term. It's almost symmetrical. 7 choose 1 would be the same thing as hold on, let me make sure I'm saying this correctly. 7 choose 3 is the same as 7 choose 4. 7 choose 2 is going to be the same thing as 7 choose 5. 7 choose 1 is going to be the same thing as 7 choose 6. And 7 choose 0 is going to be the same as 7 choose 7. So there's like a pattern of symmetry going on, which also plays into Pascal's triangle, which we're going to look at now. So Pascal's triangle is this fun little pattern that's on the front of your page. And before we talk about how to use it, let's just talk about the triangle. So you notice I've already labeled the n here, starts at 0 and goes up. But let's just talk about the pattern that we see. So we just start with a 1. And every time that we start a new row of the triangle, there's 1s on either end. So below 1, we're just going to put a 1 and a 1. Below that part, there's going to be 3 terms now. The ends are always 1s. And in the middle, we add together the 2 numbers that appear kind of triangularly above that number. So 1 plus 1 is 2. So this number becomes a 2. In the next row, the ends are 1s. 1 plus 2 is 3. 2 plus 1 is 3. In the next row, 1s on the ends. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And that pattern continues. So we can pretty easily build several rows of this triangle. And what this provides us with is actually the coefficients of our binomial expansion, right? So it plays into what these, C things are, these combinations. So think about this on the back. One of our questions was 7, choose 3, and we got 35. So think about if we come down to the 7th row here and start with, a 0 and go 0, 1, 2, 3, we get that same number, 35. So this is showing us the symmetry. And these numbers also appear at the top of the page in our actual expansion. So it went 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Take a look. That's the same numbers that showed up in this triangle. So it's giving us the coefficients. So in question example 2, we are using Pascal's triangle to find the binomial coefficients. The fact that n is 8 means we're looking for the n equals 8 row of the triangle. So I'm going to just, briefly list out all of the rows. They're on the front of the page. But if we start with 1, and then it's going to go 1, 1, and then 1, 2, 1, and then 1, 3, 3, 1. I'm just adding the 2 numbers above to get the number below. I'm going to continue with that same pattern. So it's 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, 1, 7, what is 15 plus 6, 21, 35, 35, 21, 7, and 1. And that's all the numbers that were on the front, but we can pretty easily get the next row, which is the one that we need to get the 8th n. So we have 1, 8, 28, 56, 70, 56, 28, 8, and 1. That's the one that we want. A little hint here, the second number in the row is always the n. So I'm just going to write the numbers underneath their specific, combination that's listed at the top. So it's going to be 1, and then 8, and then 28, and then 56, and then 70, and then 56 again, 28 again, 8 again, and 1 again. So there's our answers. That's all of the coefficients that we need, and we didn't have to do any of, this complicated factorial business. We didn't have to expand a binomial 8 times. We just have to list a nifty triangle, right? Pascal's triangle. So let's then apply all of this in example 3. Let's actually use this to expand a binomial. So let's say we have x plus 1 to the 3rd. Okay, so the first thing that I'm going to do is think about what is the n equals 3 row of Pascal's triangle. And that's when the second number is a 3. It's going to be 1, 3, 3, 1. So I'm going to list those numbers to the side here so that I know to use them. Okay. And now here's the pattern that we follow. Here's actually how we do this. So what we're going to be doing is kind of this, like fancy looking row of the definition back on the first page, but that looks more complicated than it really is. So here's what we really do. We grab the first coefficient, we take the first term in the binomial and raise it to the power of n. Then we take the second term, which in this case is a 1, and raise it initially to the 0 power. And what we're going to do for each successive term is use the next coefficient in line from our, Pascal's triangle, reduce the x power by 1, and increase the 1 power by 1. So it's going to be 3x squared, 1 to the first. So notice the 3 became a 2, the 0 became a 1. Next up, we take the next number in line, a 3. We take the x term and reduce the power again. We take the 1 term and increase the power again. And then we're going to take the next number in line, reduce the x power by 1, increase the 1 power by 1. And now all we have to do is simplify what this looks like. So it's going to be 1x cubed times 1, 3x squared times 1, 3x times 1, and 1 times 1 times 1. So there we go. We've expanded this without actually doing the foiling and everything. Okay, so let's try another example. This time a little bit more complicated. You have 2x minus 3 to the 4th power. Since it's to the 4th power, we're going to look for the 4 row of Pascal's triangle. It's 1, 4, 6, 4, 1. And just for reference, the first term, which we're going to call x, we could call this a, and the negative 3 this time is going to be our second term, or the b. We could call it a and b. Since x is used in the term, I don't want to say x is 2x. That sounds complicated. But anyway, okay, so we are going to expand. So let's try this again. So we start with the coefficient from Pascal's triangle. So we have a 1. We say 2x is now raised to the power of n. So it's going to be the 4. And the negative 3 starts with the 0 power. And we're going to follow that same pattern again. So we use each of the coefficients in line. We always decrease the first power and increase the second power. So we're going to have 4 times 2x cubed times negative 3 to the first, 6, 2x squared, negative 3 squared, 4, 2x to the first, negative 3 cubed, and 1, 2x to the 0, negative 3 to the 4th. So our exponents for 2x went 4, 3, 2, 1, 0. Our exponents for the negative 3 went 0, 1, 2, 3, 4. And our coefficients went 1, 4, 6, 4, 1, just like they do in Pascal's triangle. All right, so this is going to take a little bit more work. I'm going to have 2 more steps. First, I'm just going to try to do all of my powers. So we end up with 2 to the 4th, which is 16x to the 4th. And anything to the 0 power is 1, so that's just multiplied by 1. Then we have 4 times 2 to the 3rd, which is 8x cubed, times negative 3 to the 1st, so times negative 3. Next we have 6 times 4x squared. Negative 3 times negative 3 is going to be positive 9. Then we have 4 times 2x, negative 3 to the 3rd, which is going to be negative 27. And then we have 1 times 1, negative 3 to the 4th, which is going to be plus 81. So now I'm going to multiply everything together in each term. So we have 16 times 1. Pretty sure that's 16x to the 4th. And then we have minus 96x to the 3rd plus 216x squared minus 216x plus 81. So this time, in our final answer, the numbers 1, 4, 6, 4, 1 don't show up. But they did initially. They changed because one of our terms within our original binomial had a 2 in front, and the other one was a negative 3. So because those kind of mess with the coefficients, they don't look like they initially did. But it still follows the pattern. Everything still works the same. Okay, so let's try letter C. Write the expansion of the expression x minus 2y to the fourth. All right, so we're to the fourth power again, so we're going to use those same numbers, 1, 4, 6, 4, 1. So let's try it. All right, and if you're following along here, you might want to try this one on your own before you watch me do it, just to make sure you know what you're doing. But I'll write everything out. So we'll have 1, x is to the fourth, negative 2y is going to be to the 0. We have 4, x to the third, negative 2y to the first, 6, x to the squared, x to the squared, x squared, negative 2y squared, 4, x to the first, negative 2y cubed, and 1, x to the 0, negative 2y to the fourth. That's going to multiply out to x to the fourth plus negative 8x cubed y plus 6x squared times 4y squared plus 4x times negative 8y cubed plus 16y to the fourth, which becomes x to the fourth minus 8x cubed y plus 24x squared y squared minus 32xy cubed plus 16y to the fourth. There we go. That 4 doesn't really look like an exponent, but it is. It's bugging me, so I'm going to white it out and fix it. There we go. All right, so that's how you do that one. Let's take a look at letter D, right? The expansion of the expression x squared plus 4 to the third. All right, so this time we're to the third, so we're going to use 1, 3, 3, 1. We grab that from the 3 row of Pascal's triangle. And so we'll have 1 times x squared cubed times 4 to the 0 plus 3 times x squared squared times 4 to the first plus 3 times x squared to the first, 4 to the second, plus 1 times x squared to the 0 times 4 to the third. So if we multiply all this together, we have 1 times 1, x to the sixth. We end up with 3 times 4, which is 12, x to the fourth. 3 times 4 squared, so 16 times 3 is going to be 48 x squared. And then we have 1 times 4 cubed, so plus 64. All right, so in this one, you can see, the reason I wanted to end with this one is that if part of our binomial already had an x to an exponent, or any variable to an exponent, the variables in the final answer are not going to exactly match the pattern that we have discussed, right? The x exponent isn't going down by 1 in each successive term. It's actually going down by 2, but that's because we started with an x squared. So the more complicated your original binomial is, the less you're going to be able to actually see the pattern in the answer, even though the pattern really is there, right? We got 2 more questions down here. In example 4, finding a term in a binomial expansion. So this is going to allow us to find a specific term without actually calculating the entire expansion. So first up, we have find the 6th term of a plus 2b to the 8th. So first thing we're going to have to do is figure out what is going on in the 6th term here. So let's kind of think through maybe this question here. In the second term, the first part of the original binomial has already decreased by 1, and the second part has increased by 1. So in the sixth term of this expansion, think about it, the a term is going to start with an 8 exponent. So it's going to go 8, 7, 6, 5, 4, 3. So it's going to be the a to the third term. And the second part is going to go 0, 1, 2, 3, 4, 5. So 2b to the fifth. Sorry for my very large fingers on the screen. So the sixth term ends up with a 3 and a 5 as the exponents. That makes sense because 3 plus 5 is 8. And you got to kind of think through what's happening here. The only thing left is to figure out the coefficient that goes in front of all this. It ends up being 8 choose 5. And what you've realized is that the r, the number that goes down here, is the same number as the second exponent. And you can see that from the list of all of the binomial coefficients for the n equals 8 row, all the way back up here. We're talking about the sixth term. So 1, 2, 3, 4, 5, 6 is going to be 8 choose 5. It's always one less than the number term that we're on. And it corresponds to, the second exponent in our expression. So 8 choose 5, lucky for us, is already up here. It's going to be the 56. So we're going to have 56 a to the third. And let's see, 2b to the fifth. It means we have to do 2 to the fifth, which ends up being 32. And then the b is to the fifth. So the last thing we have to do is multiply 56 times 32. So we're going to get 1,792 a to the third, b to the fifth. That's officially the sixth term of the expansion. You also might get a question like letter B. Find the coefficient of the term a to the sixth, b to the fifth in the expansion of 3a minus 2b to the 11th. All right, so in the original binomial, the a has an exponent of 1 and the b has an exponent of 1. So if we're going to have a to the sixth and b to the fifth, that's going to be have to be the term that we're on. So the first part of the binomial is going to have to be to the sixth. The second part is going to have to be to the fifth. And part of the final coefficient is this 3 and -2 situation that's going on. So we got to keep track of that. I'll show you what I mean. But we have 3a that's being raised to the sixth, -2b that's being raised to the fifth. And we got to figure out what's in front of this. And remember, the exponent from the second term is the same as what we put in for C. So it's 11 choose 5. So 11C5. And we've so far today, or in this lesson, only gone to n equals 8 row. We'd have to get all the way to the 11 row. But lucky for us, there's a way that the calculator can find out 11C5 for us, so that we don't have to rely on expanding Pascal's triangle. Now, Pascal's triangle is super useful if we would need every single number in a row. We might as well just do the whole expansion. But if we're only looking for one specific number, in this case 11 choose 5, we can do it this way. So if you type in the 11, we're going to go to math, probability, and here we have NPR and NCR. We're using NCR, so I hit the number 3. So we have 11C5, and it's telling me right now that's 462. So that's all I needed here. So we have 462. 3a to the sixth is going to be 729 a to the sixth once we, do 3 to the sixth power. -2 to the fifth is going to be -32 b to the fifth. And now we have to multiply 462 times 729 times -32, and we get -10,777,536 a to the sixth, b to the fifth. Aren't you glad we didn't have to do all of this expansion by hand? That would have been a nightmare. But the question asked for the coefficient, so officially the coefficient is -10,777,536. All right, so there you go. That's the end of the notes. That should prepare you for the worksheet. Please let me know if you have any questions, and have a great day.